Hello everyone, welcome back to our blockchains course. This is going to be the second part on Corda. So we had a brief overview of Corda. We looked at what Corda transactions look like, some of the state information, high-level overview. Now we're going to go into talk about how transactions itself work, how is consensus reached, notion of notaries and how oracles are used. So we'll talk about some of those concepts in this part. So before we get there, one of the key design principles is the notion of attachments. So I mentioned about having contract code associated with legal agreements or legal pros. So they can be provided as attachments to a transaction. So if you look at a particular transaction, it not only specifies input states and output states, it can optionally provide a set of attachments. So it can refer back to the attachment can refer back to the contract code. It can refer back to external documents. Maybe this might be physical documents or scanned documents, for instance. All of these can be added as attachment to support a transaction. So these attachments can be arbitrary data in the form of zip or jar files identified by a hash, and the jar files are typically for contract code reference itself. And attachments are intended for data on the ledger that multiple peers may reuse over time. So this is supporting documentation in some sense. A transaction can reference one or more attachments, and it may contain references to data files also. So for instance, it can refer to an identity document, it can refer to a bill of lading, which is a trade document for if you're doing trade finance, for instance. And attachments are a first-class citizen for Corda. Right? In any other blockchain platform, Hyperledger Fabric and Ethereum, you can of course store attachments, but it doesn't come as a first-class citizen as part of your transaction structure itself, and that I believe has value. Right? It does make things a little easier for an application developer, especially in I think financial services where typically there are financial documents that need to be attached with a particular transaction. So now coming to the notion of transaction flows. So these transaction flows are the ones that are going to validate the sequence of steps that are needed to make a transaction legitimate and be committed on the ledgers of different peers, right? That are different transacting. So let's say we have an example where we have Alice, Bob, and Charlie in a network, and there is a one notary and one oracle. This notary, think of it as a service, so it can actually be multiple nodes there, but in logically it's a single entity. So as I mentioned, Corda, all communication is point to point, and the transactions will, along with the contract logic itself, the transactions specify a list of message recipients that are required to sign and verify the transaction. So the flow framework is then designed to orchestrate this whole thing. So it'll say that, okay, first Alice needs to sign, then Bob needs to sign, and then it can be finalized, right? And the logic that Alice and Bob use to sign this transaction can also be part of the flow, or it can also be external information. So let's go through this flow, right? So first, let's say Alice creates a transaction proposal and signs it. So it's going to take some input, transform it into some output. Input and output can be null as well, or one of them can be null, for instance. And this transaction state, along with attachments, is signed by Alice, saying, okay, here is a proposal for a transaction. Alice then sends this proposal using a point-to-point message to Bob. Bob, on receiving this proposal, can inspect it, can use any logic of their choice. This is off contract logic. This is not the contract logic itself, but it can look at the contract execution, see if the state derived by Alice is correct, and it can also use external information to see whether Alice is making, if this is a payment, for instance, whether Alice is making a payment in time, for instance. You can use all sorts of logic that is private to just Bob, and use that information to determine whether it wants to sign it or not. Once it agrees with this proposal from Alice, Bob attaches its signature also and sends it back to Alice, right? So now both have this transaction that is signed by both parties. And let's say that was all that was needed for this transaction to complete. This transaction could potentially be sent to a notary, And the notary can attest to the fact that there's no double spend that has happened, for instance, in the network. It provides certain functionality. So the notaries can also be part of the flow itself, and that is also captured before transaction finality is reached. So let's just take a flow example. So we start with Alice creating a flow, starting a flow. It creates a proposal, it creates a transaction, it signs the transaction, sends it to Bob, and that's where Bob's flow begins. So at this point, Alice's flow is suspended, it's checkpointed, and Alice is going to wait. Right? Even if Alice goes down and comes back up at a later point, its flow can resume. Bob, once it received the transaction, it's again going to inspect and verify. It then signs the transaction, and then now it has signatures from both Alice and Bob. Right? So now it can commit the transaction. It commits the transactions and can also send that transaction, the signed transaction by both parties. It sends it back to Alice. Alice again inspects and commits. So that's the full flow. So if you look at Bob's flow, this is what Bob did. Alice in between waited for Bob's signature, and then it also committed. So at this end of this, both nodes have committed. In case Alice did not receive this message, it can time out and it can ask Bob whether did you agree to it or not, and can always fetch that back from Bob. And because all of these are recorded immutably, once both of them commit, no one can go back on their transactions. Because some of these flows can be complicated, it can involve multiple parties. Here it's just a two-party flow. These flows can involve multiple parties and multiple signatures. Corda provides a library of flows for common use cases, such as atomic asset swaps, where basically assets are exchanged between parties, broadcasting to multiple peers, sending cash information. This broadcast is basically achieved through multiple unicasts, right? So agreeing multilateral deals. So for some of these common flows that are seen in financial use cases, Corda provides a library of these flows. So these flows, together with the contract logic itself, comprise the whole transaction life cycle and how transactions from proposal to commit, how they happen. So now we've only talked about the transaction execution. We need to talk about how consensus is reached between peers, right? At least peers who are transacting with each other. So Corda distinguishes two notions of consensus. One of them is validity consensus, which is to say that this transaction is actually is meeting all criteria. All the dependencies are met, all the required parties have signed. That makes the transaction valid, right? All the constraints are satisfied. So that's the validity consensus. The uniqueness consensus checks whether the state, I mentioned the UTXO state information, right? It checks whether the UTXO has not been spent, right? So the transaction output is really an unspent transaction. The transaction output is unique, right? So no one is trying to double spend in this network. So that's a uniqueness consensus. So the validity is separated away from uniqueness. We'll see how both of these are achieved. Now, one of the problems that you could see is, since there is no global broadcast and transactions are all peer-to-peer, now one of the problems that can happen is if an asset is issued by one party and it's transferred to another party B and then to C, for C to verify, let's say a month later, they will have to go through the provenance of the entire asset to see if all the transactions have been legitimate. In some ways, that's similar to how our financial transactions and other transactions also happen in the real world. For instance, let's say you're buying a new piece of land. Before you buy the land, you'll probably get the services of a lawyer, or you probably do it yourself. You'll verify whether this piece of land, this legal document, has changed hands in a legitimate manner. Maybe you'll look at 100-year history. It might have changed hands maybe dozens of times. You'll go through all that history of transactions, that whole provenance. That provenance is not recorded on blockchain. It will be great if it is. But what Corda is providing is that provenance is recorded on blockchain, but you will still have the overhead of having to go through and verify every one of those transactions, because all that is new to you, right? You are a new buyer for this piece of land. Before you buy it, you will have to verify all of those previous transactions on exchanges make sure they are legitimate before you can accept it. So that is an overhead Corda will incur, right, with especially assets that are changing hands. So now how does validation of transaction histories work, right? So let's say there is a central bank that issues a particular asset to Dan. So this is a bond that's issued. So Charlie is the central bank here. So it's signed by Charlie, and once Dan accepts it, Dan also signs it with with his signature. So that's a transaction that's recorded on blockchain. Now let's say Dan shared that same asset with Alice. So the reference to the previous bond is made, and a new state is created. So each of these, it's not the same state that's modified. It's actually a new state that's created. That's how it remains unspent. So this is now the unspent transaction. This becomes a spent transaction. Sorry, a spent state. Now this transaction is signed by both Dan and Alice. And now let's say Alice shares this with Bob. Now Bob needs to verify the whole chain. The fact that Charlie issued it to Dan, Dan then issued to Alice, all that has to be verified by Bob that, okay, this is actually a legitimate piece of state that has come from the central bank and has gone through a certain set of legitimate transactions. So I can believe this. So then I'll be willing to purchase that bond. So that then the final transaction is also signed by Alice and Bob. Now, whenever a peer is presented with a transaction containing input references that it has not seen before, then it needs to fetch all of this and verify this. So this is called walking the chain, right? This is a recursive process, and it could be time consuming, and that could act as a negative for Corda because of the fact that they don't have a global blockchain. People are not validating transactions on a continuous basis, but only on a need-to-know basis when they are accessing that asset, right? So that's an inherent trade-off that probably Corda is okay with. That's why they've designed it this way. But one thing that Corda does is this walking the chain and verifying these past transactions is done automatically by the flow framework. So the flow framework can fetch all of these transactions, verify it, and that's all automated for you, but it still incurs a computational overhead. So only required in cases where I think this negative that I'm talking about here, at least, by the way, treat it as my own perspective here. This is only needed for assets that are being transferred, right? For assets that are not transferred across users, let's say there are just two parties that are trading these assets, right? So then there is no verification that's needed. There's no walking the chain that's needed, right? So it's only when parties are seeing assets that they did not see before will this additional validation, verification, and walking the chain will be needed. Now there is also a privacy concern, as data can be leaked from the issue parties to parties further down the chain. But Corda is working through multiple alternatives to address that privacy issue. So they are looking at signing key randomization, anonymizing peers so that the peer identity is not revealed. They're also looking to use trusted platforms such as Intel SGX to verify transactions on the remote peer without transferring history. So there are many alternatives that are being considered. So the other alternative is also state reissuance. So it's as if there could be maybe a central authority that comes back in and says, yes, this is a valid state. I will issue a new state for you, right? So all that is possible. So that was the validity consensus and how peers validate whether all the history of transactions are valid. Now, the uniqueness consensus is provided by a special entity called notaries, right? In some sense, notaries are similar to Fabric, but I'll highlight similar to the ordering service in Fabric, but I'll highlight the difference as we talk through this, right? So once, let's say, Bob and Alice both sign this transaction, they can actually send it to a notary and say, hey, notary, tell us whether this transaction is really unspent, right? So the notary service is designated at a time the state is issued, right? So then for each state, at the time of issuance of the state, you can specify a notary service that will determine the uniqueness of that state, right? Let's say it's a state representing bonds. So whenever that bond is created, that state, you also specify, okay, this node is going to be the notary for this bond, and that notary will take care of ensuring uniqueness. So what the notary will do is fairly simple. If it receives a transaction and it has inputs that it has not seen before, then it will be added, and it will be the notary will sign it and say, yes, this transaction can be admitted because I have not seen the inputs of this transaction before. This is definitely unspent, and notary will sign it and send it back to Alice and Bob. Right? A special type of notary called a verifying notary will require the entire dependency chain of histories for greater assurance. So this is a verifying notary will not only do uniqueness consensus, but will also do the validation consensus that we talked about. Right? It will validate the entire history of transactions, and on top of that will also ensure that this transaction's input has been unspent. So of course the notary will only permit one of, if there are conflicting transactions that are trying to use the same input state, the notary is going to be the tiebreaker. So it's going to say, okay, this transaction will go through first, the second transaction will be invalidated. Note that many notaries can exist in a network. The notaries are created at the level of states. So based on the states, different notaries can be present in the network for different states. This can provide not only privacy, but it also provides load balancing and ensures lower latency. Right? If all the state information maintained in the network went to just one node, of course that node is going to become a bottleneck. It is also a privacy concern. So it's possible to separate out notaries for different states. Now I mentioned ordering service in Fabric. Similar to that, the ordering service in Fabric also provides some notion of uniqueness, but not really so. Right? The ordering service in Fabric just orders transactions. It doesn't do anything else. It doesn't determine whether two transactions are conflicting with each other, whether they are unique. It doesn't look at that. It simply looks at the transaction almost as a black box and says, okay, here are 100 transactions, I'm going to order them 1 to 100. That's all the ordering service in Fabric does. However, the notary in Corda actually needs to look into the input states and the output states of the transaction itself. So it has to be privy to the transaction details, and only then can it verify whether this transaction is unique. So in addition to just ordering and avoiding duplication, avoiding double spend, notaries also have to look at the data in order to be able to say that double spend has not happened. Oh, I mentioned notaries. Again, notaries is a logical concept. It can be a single node, it can be a cluster, it can implement any arbitrary logic within that service to determine this uniqueness. Right? It can be raft-based consensus, it can be Byzantine fault-tolerant consensus. So all that is possible within a notary service. So again, these kinds of consensus algorithms are similar to the ordering service. Ordering service in Fabric uses it only for ordering. Here, it does a little more in actually determining whether double spend is happening or not. Okay, so here is an example transaction flow involving a notary. So let's say there is Alice, a broker node for Alice, that's going to create a transaction. It's going to verify this transaction is well formed. It's going to sign it. It then sends it to another node. So this could be a reinsurer. So this could be Bob. So Bob then verifies this transaction. Bob also signs it, sends it back to Alice. Now both parties have signed this transaction. Alice can then send this to the notary. The notary will then determine whether this is indeed unspent. Right? Once it determines that it is unspent, it might be receiving many such transactions from multiple parties. The notary will then order all of them through either a single machine is ordering them, or multiple nodes are employing consensus to order them. It will then detect whether there are duplicates, and only if it's it's not double spent, if it's a unique transaction output, then I will sign that transaction. So the notary adds its signature and sends it back. Now this is the point when notary signs it is when the transaction is considered final, and then Alice and Bob can then commit those transactions into their respective ledgers. Likewise, Alice and Charlie, a different node, might have their own flow working on different states, but they can employ the same notary service for the same notary service to order. So then the notary service will check whether Alice is trying to send the same state to both Bob and Charlie, and will prevent Alice from double spending. So Alice can then leverage the notary service to prove to Bob and Charlie that it has not double spent this transaction. Right? So that's why the notaries are specified at the level of state. That way this notary can verify that this state is unspent. And different states can employ different notary services because there is no double spending problem across them. Notaries, in addition, can also be a timestamping authority, and transactions can include a time window to be committed. So if the transaction comes to the notary too late, the notary can refuse to sign it, saying it's outside the time window and doesn't meet the criteria mentioned in the transaction. Time windows can have a start and end time, or it can also be open-ended. So the purpose of time windows is to communicate a transaction's position in timeline corresponding to contract code. So like I mentioned previously, this is almost a DAG of states maintained by each node. But if you do want to put a timestamp on it, then the notary service is the one that's going to put a timestamp on it. And if you do want to have a timestamped ordering across different states that are present in the network, again, the notary service can help with that. Again, the notary service is also helpful in regulatory reporting to say that I performed this transaction on this date. Again, that sort of a reporting needed for compliance can also be provided by the notary service. Finally, coming to oracles, which is also a first-class principle in Corda. Oracles serve as authoritative, binding, and definitive authority on facts that are external to the network. For instance, if a smart contract depends on the share price of a particular share, right? So then there could be an oracle responsible for providing the share price, and all the peers trust the oracle to provide the same price information to all of them, regardless of who is requesting. Right? So the oracle will say, okay, anyone who is requesting the price in this time window, I will give them the same price value. Right? So that will ensure determinism of the contract, and the contract itself can be access controlled to be within that time window. Like I mentioned, you can specify that the contract has to be executed in this time window, and the oracle can also be configured to provide the same share price to all peers within that time window. So that way, contract execution can be deterministic, and contracts can also leverage facts from the outside world. So oracles are, of course, trusted entities. The peers are agreeing to trust the oracle for this service. So in financial services, again, the need for oracles, so it could be need for oracles is seen a lot, and I guess that's why Corda has incorporated oracles as a first-class principle. There are oracles that have been created, for instance, in Ethereum as a separate entity, not really part of the platform itself. But here in Corda, oracles are a first-class citizen, and oracles can be included in the flow. For instance, in the flow itself, Alice can contact the oracle, get some information, do some validation checks, and check whether it wants to sign this transaction. Oracles are implemented in a transaction using either commands or attachments. So it can be an attachment to a transaction, and there can be validation checks on that. And in this case, when an oracle is present, a signature from the oracle is needed as part of the transaction proposal. Okay, so this is the overall reference architecture for Corda. It includes all the components of Corda. We talked about how the vault stores the state information that each peer is aware of, the storage itself, the transaction flows management, identity management, key management, the network map that tells you which peers are running on which IP addresses. How do I send messages to a particular bank, for instance? How should I address them? It can refer to notaries. It can be part of a messaging. It will have a messaging service that connects to other nodes. And of course, all the communication with the Corda node happens through an RPC client, and can also you also have a web server along with it. The user-defined Corda application includes all of this, right? It includes services, includes the contract, the state information, the transaction flows referring to these states. All of that is captured as part of the Corda application. And the Corda application can also refer to existing flows, refer and utilize existing flows that are already defined as libraries by Corda. So that's roughly the high-level overview architecture picture of Corda. So with that, we come to the conclusion of this lecture. Here is a short video on Corda oracles, right? And why Corda oracles are needed, how they function. It's a very short video that you can perhaps take a look at to get a sense of how oracles work in Corda. So I hope with that you've got a good overview of the Corda architecture. We've looked at a bunch of these platforms now. I hope you're appreciative of the fact that there's a lot of innovation going on in different platforms. There are different design principles they're all starting with, different constructs that they are creating to address the enterprise requirements of many of these blockchain applications. So some of these networks utilizing these platforms are just starting to come into production, and it's really a very exciting time for enterprise blockchain applications to really make a big impact in all of our lives. So with that, thanks a lot. It was great having you with us in this course, and I hope you enjoyed it as well. Talk to you soon. Bye.